Hey, when a fluid moves through a pipe and therefore through a bend or an elbow, it exerts a force on that particular bend. Therefore, in our discussion today, we are going to look at that force a fluid will exert on a bend in a pipeline, and we have a guiding question which says that a 45-degree reducing bend is connected in a pipeline. The diameters at the inlet and outlet of the bend being 600 and 300 respectively. Find the force exerted by the water on the bend if the pressure intensity at the inlet to the bend is 8.29 Newton per square centimeter and the rate of flow of water is 600 liters per second. Let us look at this drawing of ours. This drawing, when we look at solution of this problem, this drawing is just simplifying the whole scenario, giving us forces that are in play. We have a horizontal force due to pressure at P1. In other words, at section 1, we have pressure P1, and at section 2, we have pressure P2, and other parameters like area and velocity are also named according to the section in which they are or in which the fluid is moving. So we see that this fluid is moving through a pipe that has got a bend which is bending at 45 degrees. So it bends at 45 degrees, and therefore we are required to find the force that is exerted, that the fluid exerts on this bend. And therefore, to proceed with this particular problem, we look at a force P1 is moving in the direction of flow, whereas due to this pressure at section 2, we will have a force due to this pressure P2, but in the opposite direction. Remember, according to the third Newton's law of motion, that for every action there is always an equal and opposite reaction, and therefore you will see that the force that is here due to pressure P2 is opposing the force due to pressure at section 1. Whereas the velocity is in that direction V2, you see the force due to this pressure is opposing the direction of the force due to P1. Let us therefore assume that that force has got a component in the x direction and a component in the y direction. So if it has a component in the x direction and the y direction, we will find that the net force exerted by the fluid on the bend is equal to the rate of change of momentum of the fluid, because we have forces that are in play here. We have the force due to pressure, we have the force that the fluid exerts on the bend. Likewise, this bend, if it is in the x direction, the component of this force will be negative Fx, because for every action there is an equal but opposite reaction. So if the fluid exerts a force Fx on the bend will exert the same force on the fluid by magnitude of Fx, but in the opposite direction. Therefore, if we are to consider it, it will be in the negative direction. Therefore, we have a net force exerted by the fluid on the bend, and it is equal to the rate of change of momentum of the fluid. We know the rate of change of momentum of the fluid according to second Newton's law of motion. We see that the rate of change of momentum is equal to the force. In other words, according to second Newton's law of motion, it says that the rate of change of momentum of a body is directly proportional to the force applied and takes place in the direction in which the force acts. Therefore, it means if we look at the forces that are being exerted by the fluid on the bend, they will always equal to the rate of change of momentum of the same fluid. So As we have said that this Fx is a force exerted by the fluid on the bend, and the bend will exert an equal but opposite force. The same applies to Fy, which is the component of this force in the vertical direction. Therefore, the net force will be, remember, due to pressure at section 1, it will be P1 times A1, because we know that pressure is equal to force out of area, meaning that the force due to that pressure will be pressure times area at that section. Since this pressure is acting in the opposite direction, therefore the force it exerts will also act in the same direction. Therefore, it will be minus P2A2, but because it's we are considering this force, it is at an angle, it is acting at an angle of theta to the horizontal, and therefore if we were to resolve it horizontally, it will be P2A2 cos theta. Then minus Fx, which is the force the bend exerts on the fluid. Therefore, the force, of course, this is it would have been plus, then minus Fx, whereby Fx is the force the fluid exerts on the bend, but the minus Fx is the force that the fluid exerts on the minus Fx is the force the bend exerts on the fluid. So P1 is equal to 8.29 Newton per square centimeter, but we can convert it into standard units of Newton per square meter, and this is equal to that because we know in 1 centimeter we have 10 to the power negative 2 meters. Therefore, if we square, that means 1 square centimeter is equal to 1 out of it is equal to 1 times 10 to the power negative 4 square meters. Therefore, if we convert, we will have that particular figure. We need to also determine the area at section 1. The cross section will be pi d1 squared out of 4. That is the formula for area of the cross section, and we will have 0.2827 square meters. Then the area at section 2 is pi d2 squared out of 4. The diameter is 0.3 or 300 millimeters, and the cross-section area would be that. Let us also look at the continuity equation. The continuity equation, when we consider sections 1 and 2, the flow rate at section 1 will equal to the flow rate at section 2. Therefore, A1 V1, area at 1 times the velocity at 1 should be equal to area at 2 times the velocity of flow at 2. Of course, these are mean velocities across the section. Then therefore, V1 will equal to Q divided by A1, and since Q, the flow rate is 600 liters per second, or 0.6 cubic meter per second, then it will be V1 will be 0.6 divided by 0.2827, and this would give you 2.122 meters per second. Then velocity at 2 will also be Q divided by A2, which is equal to 0.6 divided by 0.07069, and it gives you 8.488 meters per second. Then we needed to also apply Bernoulli's equation between sections 1 and 2 in order to determine the pressure at 2. Because if we don't have pressure at 2, then we cannot proceed with whatever we need. Therefore, P1 divided by rho g plus V1 squared out of 2g plus Z1 is equal to P2 out of rho g plus V2 squared out of 2g plus Z2. Since the pipe is on a ground, on a horizontal ground, then Z1 is equal to Z2. Therefore, P2, reorganizing this equation and making P2 the subject of the formula, would bring us to substitution of all these values. We already have P2, we have V1, we have V2, so, and G is 9.81. The density of the fluid, since it is water, it is 1,000. So 1,000 times 9.81, you would get that value. 2 times 9.81 will get 19.62, and therefore P2 would be equal to 5451.37 pascals, or just in newtons per square meter. Therefore, if we were to substitute in that equation that looks for the net force acting on the bend, of forces acting on the fluid, then we find that actually 8.829 times 10 to the power 4 times the area, of course this is the pressure at section 1, times the area minus the force that the fluid exerts on the bend, then minus 5.452, which is the pressure at the section 2, times 10 to the power 4 times 0.07069, which is the area at section 2, then times the component, the component of the cos that tells us this has been resolved horizontally, and therefore the net force would be that value minus fx minus 2725.2. Therefore, we can call this one equation star. And we also talk about the rate of change of momentum. The rate of change of momentum of the fluid is equal to density times Q into V2 cos theta minus V1. If we substitute in those values, we will get 2327.95. The flow rate is 0.6, the density is 1000, the velocity V2 is 8.48, the theta is 45, minus velocity 1, which is 2.122. And if we look at the two from equation star and star star, then when we solve for x, for fx, our value would come to fx equal to 199.06.43 Newton. Then this is the force on the bend as in the x direction. We need to also look for the net force in the vertical direction on the same bend. Then therefore it will also equal to the rate of change of momentum in the of the fluid, the rate of change of momentum of the fluid in the vertical direction. Since P1 is horizontal, therefore it's if I would put it, still it would cancel out. P1 A1 minus F1 minus Fy, remember this will go to 0 because this force is horizontal and therefore it doesn't have the vertical component. So minus Fy minus P2 A2 sine theta. Since it is being resolved vertically, then it will take a sine, is equal to rho Q, which is the rate of change of momentum, then into V2 sine 45 minus V1. But remember, since it is also resolved in vertical direction, since V1 is horizontal, then this will also go to 0. Therefore, we remain with Fy, which is equal to rho Q V into V1 minus V2. Remember, this is equal to 0. Then minus P2 A2 sine theta. So if we substitute in our values, 1000 times 0.6 into 0 minus 8.488 sine 45 degrees, then minus 5.452 times 0.07069. Remember that is the area at section 2. Then sine 45. Remember this is times 10 to the power 4, so we multiply by 10 to the power 4. Fy would be equal to negative 6326.3 Newton. Therefore, if we use the parallelogram law of forces or Pythagoras theorem, we find that F is equal to Fx squared plus Fy squared under root, and our value of F is equal to 20887.53 newtons. We need to also determine the direction with which this force makes with the horizontal. Then we can get it by giving its component. We know since the Fy is negative, then this force is Fy is pointing vertically downwards. Since this is positive, Fx is positive, then it is pointing in the positive x direction. Therefore, if we use SOHCAHTOA and tan equal to opposite of adjacent, then we find that theta will equal to arctan. Since the opposite is Fy, then the adjacent is Fx, then the angle would automatically equal to 17.63. So that is the force and that is the direction. Thank you so much for watching.